Hello everyone, and today in this video I'll explain some of the basic concepts about vectors. So as you can see, I've written down a couple of topics that we'll talk about. We'll talk about what a vector is, the math you can do with it, some of the functionality that vectors have, and then what they're used for. So first up, what is a vector? A vector can actually be a lot of things. You could write it down like this. This is how it's done in linear algebra, and then you could just give it some components. Usually these are x, y, and z. These can be coordinates on a screen. They can also be just raw data. If you're using vectors to represent data, you can also just a vector object v equals a large string of numbers. So this is basically just an array that you can then perform operations on. We'll just look at them like their coordinates. So in the previous video, we then saw in the library that each vector struct has three components: an x, y, and a z. For example, you could have a vector called v, and it would equal 3, 2. On a graph, it would then just be, so this would be that vector over here, the v vector, but simply on a plane. So now we'll look at some vector math, because if you have a vector called v, for example, which is 2, 2, and then you have a vector u, I know they look the same, but and this one is 3, 2, for example, you can add them up, and then these vectors, they're just vectors that only have an x and a y component. You could also just imagine them as vectors having an x, y, and z component, but just with the z component set to 0. So if we're working with 2D textures or 2D coordinates, we'll only use the x and y coordinates, obviously. But we can add v and u to get a vector with these components. The x is 5 and the y is 4. So you can obviously just display these coordinates like this. So if we were to represent these two vectors on a graph, we get this. Now when we add these up, we get the resulting vector of 5, 4. Right? So we can also just draw this one 5 and then 4 over here, which you might notice that this one is the same as simply putting the start of one of these two vectors on top of each other. Right? If we were to take this u vector and put the beginning of the u vector, which is at 0, 0, on top of here, of the end of the v vector, we'd simply get this, which is also the same for the v vector. If we were to replace this v vector over here, you would get this. So you can very easily visualize addition and stuff like that. Now we can also subtract these two vectors. In this case, we would get -1, 0, which would basically mean something like this, right? So -1. So we would have a vector pointing towards over here. In this case, we are subtracting v from u from v. So what we can do is we can simply put the end of the u vector at the end of the v vector, and then if we were to draw this u vector, we would get this, right? We would reach the -1, 0 position. But what we're basically doing is just adding up the v and the u vectors, but with the u vector turned, right? So this is the resulting vector that you can turn over here. So this would be the exact same thing as simply doing v plus -u, and you would also end up with the coordinate -1, 0. Then we can also perform scalar operations on vector. These are also very simple. Imagine you have a vector with components 3, 3. What you can do is you can multiply this vector by 2, for example. And what this does is it just scales the vector, so you end up with a vector of 6, 6. Right, this makes sense. We can also visualize this quite easily. Imagine if we had a vector with coordinates 1, 1. If we were to scale this by 2, what would happen is just it gets scaled by 2, like so. That's a scalar operation. You can also divide a vector by 2. If we were to divide this one by 2, we'd end up with we would obviously end up with a smaller vector, right? So you can also multiply two vectors. So if you had a vector 2, 2, for example, and you were to multiply this by 3, 2, you just multiply each component, so you will end up with a vector of 6, 4. Here we have a vector v with coordinates 2, 3. You can get a lot of data from the vector. You could, for example, get the magnitude of a vector, which you can note like this, like taking the absolute value from a vector. What the magnitude essentially is simply the length of this line you see here. So we can then use Pythagoras to solve for v, right? So we have a length of 2, a height of 3. Calculating the magnitude is very easily. Just do 2 times 2 plus 3 times 3 squared will basically give you the length of v, or equals the magnitude of v. Also do with vectors is normalize the vector. This is very useful because this will allow us to set the magnitude of a vector. What normalizing a vector does is simply it takes the magnitude of a vector and sets it equal to 1. How you can do this is very easily. Just take each component of a vector, so the x, y, and z components, and you divide them by the magnitude. This will result in the vector still pointing in the exact same direction, but simply having a magnitude equal to 1. And a magnitude equal to 1 is also known as a vector of unit length. When we can normalize a vector, we can also just set the magnitude. Let's say we have this vector here, you know, the original v vector, and we wanted to have a magnitude of 10. What we can do is first just normalize the vector and then multiply each component by 10. This will simply result in our vector being having a magnitude of 10. Then some things you can use vector objects for. You can use vector objects to simply represent colors, right? A vector object consists of an x, y, and a z, but you can just easily modify this and give it an x, y, z, and an alpha, for example. Now you basically just have a color structure. You can do a lot of things with, right? Let's say that you're doing some sort of calculations with these colors. You want them to progress slightly or whatever. You could use some functions in the library. For example, limit. I think it's called limit component of this vector, right? Of your color vector between 0 and 255, for example. What vectors are also used for are positions, velocity, and also acceleration, right? That's also what they're often used to represent. We'll go over this in more detail later on when we actually get to this stuff, right? To bodies and whatever that we have to simulate. Because basically what we'll do is we'll create some sort of transform component that keeps track of the positions, velocity, and acceleration. And these things are also all just vectors that we'll just add to each other. Then lastly, we'll also use them as forces very heavily throughout the series. There's also a function in the library called just limit magnitude. So to summarize, a vector object is simply holds some data, right? This can be positions, coordinates, colors, whatever. You can add multiple vector objects up, right? So you can do this plus another vector, and when you just add or subtract or whatever, add or subtract each component with each other. You can multiply vectors. You can also take a vector, in this case v for example, and multiply it by a number. This is called a scalar operator. You can take the magnitude of a vector. You can get the heading of a vector. The heading function in the library will simply return the heading, right, the degree, the radian, basically of where this vector is pointing to, right? So if you had a vector 2, 2, it'll basically just give us the direction in radians. The magnitude is simply the force, I guess, of a vector. And this is really all that you have to know about vectors. They're not at all that complicated, and you'll also see vectors represented like this. You know, they have like many different components. These you won't be able to make with the vector library, but you will be able to make these with the matrix library that we'll go over in the next video. But yeah, I hope you enjoyed this video, and I'll see you next time.